At the heart of modern physics, two theories describe the universe with astonishing precision, yet they cannot agree on what happens when gravity becomes extreme. On one side stands Einstein's general relativity, a theory that treats space and time as smooth, continuous, and deterministic. In Einstein's universe, black holes are simple, in a brutal way. Whatever crosses the event horizon is gone forever. On the other side stands quantum mechanics, a theory built on uncertainty, probability, and information. In the quantum world, information is sacred. It can change form, become scrambled, or hidden, but it can never be destroyed. For decades, these two frameworks have both been correct, and yet fundamentally incompatible. This conflict is known as the information paradox, a silent war between the laws that govern the very large and the very small. In this documentary, we will explore how this paradox emerged, why it threatens the foundations of physics, and how black holes became the battlefield where Einstein's geometry collides with quantum law. We will trace the story from the birth of black holes in relativity, through Stephen Hawking's shocking discovery of black hole radiation, and into modern ideas involving holography, entanglement, and the nature of reality itself. Nothing here is speculative fiction. Every concept is rooted in real equations, real experiments, and decades of scientific struggle. If you enjoy calm, long-form journeys into the deepest questions of the universe, consider subscribing for more space documentaries like this, because this is not just a disagreement between theories. It is a war over whether the universe remembers or forgets. The story of the information paradox begins long before black holes were understood as physical objects. It begins with a deeper divide, a divide in how reality itself is described. At the start of the 20th century, physics split into two radically different languages. One language described the universe as smooth, continuous, and geometric. Space and time formed a single fabric, bending under the influence of mass and energy. Motion was deterministic. Causes led cleanly to effects. This language became general relativity, Einstein's theory of gravity. The other language described the universe as discrete, probabilistic, and fundamentally uncertain. Energy came in packets. Particles behaved like waves. Observation altered outcomes. This language became quantum mechanics. For decades, both languages worked perfectly, as long as they were not forced to speak about the same thing. Relativity excelled at describing stars, planets, galaxies, and the large-scale structure of the universe. Quantum mechanics excelled at describing atoms, particles, and the microscopic world. Each theory was astonishingly accurate within its own domain. The trouble began when gravity and quantum effects were forced into the same place. Black holes became that place. Einstein's equations predicted black holes as early as 1915, but even Einstein himself doubted they were real. They seemed too extreme, too pathological, a region where space collapses, time slows to a halt, and nothing escapes felt like a mathematical artifact, not a physical object. But as decades passed, evidence mounted. Stars orbited invisible masses, X-ray emissions revealed accretion disks, gravitational waves confirmed mergers. Black holes were not theoretical curiosities, they were real. And once they were real, physics could no longer avoid asking what happens at their deepest boundary. In Einstein's framework, black holes are brutally simple. Once matter crosses the event horizon, it is causally disconnected from the rest of the universe. No signal, no force, no influence can escape. The information carried by that matter is effectively removed from the universe forever. From the standpoint of relativity, this is not a problem. General relativity does not care about information. It cares about geometry. The equations remain consistent even if matter vanishes behind a horizon. But quantum mechanics does care. Quantum theory is built on a foundational rule called unitarity. This rule states that the evolution of a closed system preserves information. If you know the state of a system at one time, you can in principle reconstruct its past or future, destroy information, and quantum mechanics collapses. This is not a philosophical preference. It is a mathematical requirement. Without unitarity, probabilities stop adding up. Cause and effect lose coherence. The theory stops making sense. For a long time, physicists assumed black holes would somehow respect quantum rules once quantum gravity was fully understood. The details were unclear, but optimism prevailed. Then Stephen Hawking changed everything. In the 1970s, Hawking applied quantum field theory to the curved space-time around the black hole. His calculation was careful, conservative, and based on accepted physics. He discovered that black holes are not perfectly black, they emit radiation. This radiation, now called Hawking radiation, arises from quantum fluctuations near the event horizon. Particle-antiparticle pairs form spontaneously, one falls in, the other escapes. Over immense timescales, the black hole loses mass and eventually evaporates. This was a revolutionary result. It unified gravity, quantum mechanics and thermodynamics in a single prediction. Black holes had temperature, they had entropy, they behaved like thermodynamic objects. But hidden inside this triumph was a catastrophe. Hawking radiation appeared completely thermal. It carried no information about what fell into the black hole. Every particle looked statistically identical, regardless of the black hole's history. When the black hole fully evaporated, all that remained was featureless radiation. The information was gone, not hidden, not scrambled. This conclusion horrified physicists. If Hawking was right, then black holes violate unitarity. Quantum mechanics would not be universally valid. The universe would fundamentally forget. Hawking himself embraced this conclusion. He argued that information loss was real and that quantum mechanics must be modified to accommodate it. This marked the opening of the war. On one side stood general relativity, which had no objection to information loss. On the other side stood quantum mechanics, which could not survive it. Both theories had overwhelming experimental support. Neither could be casually discarded. The information paradox was born. For years, the debate simmered. Some physicists hoped Hawking's calculation was incomplete. Others suspected that information might leak out in subtle correlations. But no concrete mechanism existed. The paradox deepened as black hole thermodynamics became more precise. Jacob Bekenstein showed that black holes have entropy proportional to their surface area, not their volume. This was shocking. It suggested that information content scales in ways completely unlike ordinary matter. Why should a black hole's information be stored on its surface? Relativity offered no answer. Quantum mechanics whispered that something deeper was happening. As the years passed, the paradox refused to go away. Attempts to modify quantum mechanics led to inconsistencies elsewhere. Attempts to preserve unitarity seemed to violate relativity or causality. Every solution broke something fundamental. This was not a technical glitch. It was a structural conflict. At its core, the information paradox exposed a philosophical tension that physics had avoided for decades. General relativity treats space-time as fundamental. Quantum mechanics treats information as fundamental. Black holes forced a choice. If space-time is fundamental, information can be lost. If information is fundamental, space-time must change. There was no middle ground. The paradox also revealed a deeper discomfort. Physics had assumed that reality must remain describable in a single unified picture. Black holes challenged that assumption. An outside observer sees matter freeze and fade at the horizon. An infalling observer experiences nothing special. Both descriptions are valid, they cannot be combined. This was not merely strange, it was destabilizing. If physics allows mutually incompatible descriptions of the same event, what does reality mean? The information paradox was no longer just about black holes. It was about whether the universe has a single objective narrative. Einstein's theory insisted on a smooth geometric story. Quantum mechanics insisted on a probabilistic informational one. Black holes forced them to collide. The war intensified in the 90s with the rise of string theory and quantum gravity research. New ideas emerged: extra dimensions, holography, entanglement as geometry. These ideas were radical, but they shared a common theme. Space-time might not be fundamental after all. The most shocking proposal was the holographic principle. It suggested that all the information inside a region of space can be encoded on its boundary. A three-dimensional world could emerge from a two-dimensional surface. This was not science fiction. It arose directly from black hole entropy calculations. If true, it meant Einstein's space-time was an emergent illusion, a macroscopic approximation built from underlying quantum information. This idea terrified and excited physicists in equal measure. It offered a way to save quantum mechanics by sacrificing the fundamentality of space-time. But accepting it meant rewriting intuition itself. The information paradox had transformed from a technical puzzle into a revolution. It demanded that physics decide what it values more: geometry or information, continuity or unitarity, intuition or consistency. Einstein had given the universe shape. Quantum mechanics had given it memory. Black holes forced physics to ask which mattered more. As the battle lines hardened, one thing became clear. The paradox would not be resolved by small adjustments. It required a conceptual leap. Either information truly disappears, shattering quantum mechanics, or space-time is not what it seems. There was no third option. This is why the information paradox is not a footnote in physics history. It is one of its central turning points. It is where two of the most successful theories ever created discovered that they cannot both be right in the same universe unless something far deeper is true. In the next part, we will follow how physicists tried to escape this deadlock. We will explore the first serious attempts to preserve information without destroying space-time, and why each attempt revealed new and unsettling consequences. Because once the war between Einstein and quantum mechanics began, there was no path back to comfortable answers. The moment Stephen Hawking announced that black holes evaporate, the information paradox ceased to be abstract. It became unavoidable. Physics was forced to confront the possibility that one of its deepest principles was wrong. What followed was not a single debate, but a prolonged struggle spanning decades. At first, many physicists believed Hawking's conclusion must be incomplete. The calculation was elegant, but it relied on approximations. Quantum fields were treated on a fixed space-time background. Gravity itself was not quantized. Perhaps information escaped in ways too subtle to detect within Hawking's framework. This hope defined the first phase of the war. The most conservative response was to assume that information somehow leaked out with the radiation, hidden in correlations too delicate to be captured by Hawking's original analysis. According to this view, Hawking radiation was not truly thermal. It only appeared so because the correlations were unimaginably fine-grained. In principle, information was preserved. In practice, it was invisible. This idea was comforting, but it lacked proof. For years, no calculation showed how information could escape without violating locality or causality. Hawking radiation emerged from just outside the event horizon. The interior of the black hole remained causally disconnected. How could information from inside influence the radiation outside? General relativity forbade it. This led to a more radical proposal. Maybe information really was lost. Hawking himself championed this position. He argued that black holes introduce a fundamental irreversibility into nature. Pure quantum states evolve into mixed states. Unitarity is broken. This was a shocking claim. Quantum mechanics had survived every experimental test. It was the foundation of modern physics. Modifying it would ripple through every field, from particle physics to chemistry. But Hawking was not reckless. He believed that quantum mechanics was incomplete, and that gravity revealed its limits. Just as relativity had replaced Newtonian mechanics, perhaps a deeper theory would replace quantum unitarity. This proposal split the community. Some physicists were willing to sacrifice unitarity. Others saw it as non-negotiable. To them, abandoning unitarity meant abandoning the predictive power of quantum theory itself. The war lines hardened. Meanwhile, black hole thermodynamics added fuel to the fire. The entropy of a black hole scaled with its surface area, not its volume. This was not just strange, it was revolutionary. In ordinary systems, entropy measures the number of microscopic configurations. It scales with volume. A black hole violated this intuition completely. This suggested that the degrees of freedom describing a black hole were not distributed throughout its interior. They were somehow encoded on the horizon. But encoded how? General relativity had no answer. Quantum mechanics hinted at a deeper structure, but it was unclear how to make this precise. In the 1990s, a breakthrough emerged from string theory. Physicists began studying certain idealized black holes that could be described using strings and branes. In these special cases, they were able to count the microscopic states responsible for black hole entropy. The result was astonishing. The entropy matched Bekenstein's formula exactly. For the first time, black hole entropy had a microscopic explanation. It came from quantum degrees of freedom. Information was real. It was countable. This was a turning point. If black hole entropy could be explained by quantum microstates, then information seemed to be preserved, at least in these models. Hawking's conclusion began to look less inevitable, but there was a catch. These calculations applied only to highly idealized black holes, often in extra dimensions, far removed from realistic astrophysical black holes. It was unclear whether the lesson generalized. Still, the implication was powerful. Black holes might not destroy information after all. This fueled a new wave of ideas. The most influential was the holographic principle, proposed independently by Gerard D.H. Hooft and Leonard Susskind. It suggested that all the information in a region of space can be encoded on its boundary. This was not metaphorical. It was a literal statement about degrees of freedom. If true, it meant the interior of a black hole was not an independent region of reality. Everything inside could be described by information living on the horizon. This idea directly challenged Einstein's view of spacetime. In general relativity, spacetime is fundamental. In holography, spacetime is emergent. It arises from underlying quantum information. This was a radical shift, but holography offered a way out of the paradox. If information is stored on the horizon, then Hawking radiation could carry it away without violating causality. The information would never need to escape from the interior. It was never there in the first place. This reframing softened the conflict between relativity and quantum mechanics. Yet holography came at a cost. It required abandoning the idea that space-time is fundamental. It required accepting that the interior of a black hole might be an emergent illusion. This was deeply unsettling. Einstein's theory had taught us that space-time is the arena of reality. Holography suggested it was a projection. The war had escalated. At the same time, new paradoxes emerged. One of the most troubling was the problem of entanglement. Hawking radiation is entangled with the interior of the black hole. As radiation escapes, entanglement builds. Eventually, if information is preserved, the radiation must become entangled with earlier radiation instead. But quantum mechanics forbids a system from being maximally entangled with two independent systems at once. This is known as the monogamy of entanglement. Something had to give. Either information was lost or the smoothness of space-time at the horizon was destroyed. This led to the infamous firewall paradox. According to the firewall argument, if information escapes in Hawking radiation, then the horizon cannot be smooth. An infalling observer would encounter high-energy quanta at the horizon, a firewall. This violated Einstein's equivalence principle, which states that free-falling observers experience nothing special at the horizon. The paradox had mutated. Saving quantum mechanics seemed to destroy general relativity at the horizon. Saving general relativity seemed to destroy quantum mechanics globally. The war between Einstein and quantum mechanics had reached a new level. Every attempted resolution sacrificed something sacred. Physicists were forced to confront a grim possibility. Perhaps no single description of black holes could satisfy all principles simultaneously. Perhaps reality itself allows mutually incompatible descriptions depending on perspective. This idea, known as black hole complementarity, suggested that no observer ever sees a violation of physics, even if global descriptions appear inconsistent. From the outside, information is preserved in radiation. From the inside, space-time is smooth. No single observer can verify both. This was a clever compromise, but it raised philosophical concerns. Was physics abandoning objective reality? Or was it discovering that objectivity itself is contextual? The information paradox had transformed into a question about the nature of truth in physics. As the years passed, the paradox resisted closure. Each solution illuminated one corner while casting another into shadow. What was clear, however, was that the conflict was not superficial. It was not about technical details or missing equations. It was about what physics considers fundamental. Einstein had built a universe out of geometry. Quantum mechanics had built a universe out of information. Black holes demanded a choice. Either space-time is fundamental and information can be destroyed, or information is fundamental and space-time must emerge from something deeper. The war between these ideas reshaped modern theoretical physics. It pushed the field toward quantum gravity, holography, and information theory. It forced physicists to think about entropy, entanglement, and complexity as foundational concepts. And it made one thing unmistakably clear. The information paradox was not a problem to be patched. It was a signal that the universe is structured in a way that neither Einstein nor early quantum mechanics fully anticipated. In the next part, we will explore how this signal led to one of the most radical shifts in physics, the idea that space-time itself may be built from information and that black holes are not places where reality ends, but where its deepest structure is revealed. As the information paradox deepened, it became clear that the conflict was no longer about black holes alone. It was about the structure of reality itself. Theories were not merely disagreeing on details, they were disagreeing on what the universe is made of. At the center of this shift was a growing realization: space-time might not be fundamental. This idea did not emerge suddenly. It arose slowly, from a series of clues that all pointed in the same unsettling direction. Black hole entropy scaling with surface area, the success of microscopic state counting in string theory, the strange effectiveness of holographic descriptions, each suggested that the geometry of space and time could be a secondary phenomenon emerging from something deeper. That something increasingly looked like information. In ordinary physics, information is often treated as abstract, a description of a system, not a physical ingredient. But black holes refused to respect this distinction. Their entropy behaved like a real physical quantity. It obeyed thermodynamic laws, it determined temperature. It constrained evolution. Information was not just bookkeeping, it was physical. This realization inverted the hierarchy of theories. Instead of space-time containing information, information might be generating space-time. If that were true, then Einstein's equations would describe an emergent structure, not a fundamental one. General relativity would be a macroscopic approximation, like fluid dynamics or thermodynamics, accurate, powerful, but not ultimate. This was a radical reinterpretation of one of the most successful theories ever written, but the evidence kept accumulating. One of the strongest pieces came from holography. In certain mathematical models, physicists showed that a gravitational universe could be fully described by a quantum theory living on its boundary. The bulk space-time, with all its dimensions, curvature and dynamics, emerged from a lower dimensional system with no gravity at all. This was not an analogy, it was an exact equivalence. Every process in the bulk had a precise counterpart in the boundary theory. Black holes, evaporation, entropy, all of it could be described without referring to space-time as a fundamental entity. Information was doing the work. This was deeply unsettling because it contradicted centuries of intuition. Space and time feel more real than anything else. They appear continuous, omnipresent, unavoidable. To suggest they are emergent felt like suggesting that the ground beneath reality is an illusion. Yet the mathematics was relentless. In holographic models, information was never lost. Black hole evaporation was unitary. The paradox dissolved, not because information escaped in a clever way, but because it was never trapped in space-time to begin with. From this perspective, the event horizon was not a one-way barrier in a fundamental sense. It was a feature of an emergent description. The deeper description had no such boundary. This did not mean that observers could see through horizons or retrieve lost objects. It meant that the ultimate accounting of information occurred at a level where horizons did not exist. The implications were enormous. If space-time is emergent, then locality, the idea that interactions occur at specific points, is also emergent. Quantum mechanics allows non-local correlations. Entanglement links distant systems instantly without transmitting signals. In a space-time first picture, this non-locality feels mysterious. In an information-first picture, it feels natural. Distance becomes a measure of how strongly systems are entangled, not how far apart they are in space. Black holes, with their extreme entanglement structure, became laboratories for this idea. The information paradox thus shifted from being a contradiction to being a clue. It was pointing toward a deeper framework where the apparent conflict between relativity and quantum mechanics dissolved, but accepting this framework required letting go of something precious. It required letting go of the idea that there is a single, universal space-time description that applies everywhere. Instead, space-time would be a useful, approximate language, one that works when information is organized in certain ways and breaks down when it is not. This explained why the paradox was so stubborn. Physicists had been insisting on describing black holes using space-time concepts, even when space-time itself was failing as a description. Once this was recognized, the paradox began to soften. The black hole interior was no longer a mysterious region where information went to die. It was a feature of a particular description, one that emerged for infalling observers but had no independent existence at the fundamental level. The exterior description, where information slowly reappears in radiation, was another emergent perspective. Neither description was wrong, neither was complete. This was a profound shift in how truth was understood in physics. Truth was no longer a single picture. It was consistency across perspectives. This idea challenged classical realism, but it was not arbitrary. It was demanded by the mathematics. The information paradox forced physics to confront the possibility that reality does not admit a single global description that is valid for all observers at once. This idea already existed in embryonic form in relativity, where simultaneity depends on the observer. Black holes extended this dependence to information itself. The interior and exterior of a black hole could not be described simultaneously in a single space-time picture without contradiction, but they could coexist as complementary descriptions. This complementarity was not a philosophical escape hatch, it was a structural feature of the theory. Once accepted, many apparent paradoxes lost their force. The firewall problem, for example, depended on assuming that entanglement relationships had to be described in a single global framework. In an emergent space-time picture, this assumption fails. Entanglement can reorganize itself in ways that preserve consistency without producing observable catastrophes. This did not mean all problems were solved. The emergent space-time picture raised new questions that were just as deep. How exactly does space-time emerge from entanglement? What determines which description applies to which observer? How does classical geometry arise from quantum correlations? These questions remain active areas of research. But the direction was clear. The information paradox had revealed that Einstein's space-time and quantum mechanics information were not enemies. Einstein's equations described the behavior of emergent geometry. Quantum mechanics described the underlying information dynamics. Black holes were the places where the layers peeled apart. This realization also changed the meaning of singularities. In classical relativity, singularities mark points where physics breaks down. In an emergent picture, singularities mark the breakdown of space-time as a description, not the breakdown of physics itself. Something continues beyond the singularity, but it is not describable in space-time terms. This reframing stripped singularities of their apocalyptic flavor. They became signals that a different language was required. The information paradox thus acted as a translator between languages. It showed where space-time language fails and where information language must take over. This was not a defeat for Einstein, it was a generalization. General relativity remains correct within its domain, just as Newtonian mechanics remains correct within its own. The paradox revealed the boundary of that domain. Einstein's geometry is the physics of organized information. Quantum mechanics is the physics of information itself. Black holes sit at the boundary where organization collapses. This insight also explained why black holes are so efficient at scrambling information. They are regions where space-time organization breaks down most completely. Information is redistributed across degrees of freedom that no longer resemble spatial structure. From the inside description, space-time appears smooth. From the fundamental description, space-time is not there at all. This duality is not contradictory, it is layered. The information paradox forced physics to adopt this layered view. It taught physicists that demanding a single, intuitive picture of reality may be the wrong demand. Nature may operate in ways that require multiple, mutually exclusive descriptions that nevertheless agree on all observable outcomes. This was a humbling lesson. It suggested that human intuition, shaped by a world of stable objects and slow information flow, is not a reliable guide at extreme scales. Black holes are where intuition fails first and most dramatically. They expose the scaffolding beneath reality. As this perspective solidified, the war between Einstein and quantum mechanics began to look different. It was no longer a war to the death. It was a negotiation about hierarchy. Which theory is fundamental? The answer emerging from the paradox was clear. Quantum mechanics, with its insistence on information preservation, sits deeper than space-time. Einstein's geometry emerges from it in the appropriate limits. This answer did not come easily, and it did not come without cost. It required abandoning the idea that space-time is the stage on which physics plays out. Instead, space-time became part of the play. The information paradox had not been solved by clever tricks or hidden mechanisms. It had been solved by changing what physics considers real. In the next stage of this story, we will see how this shift led to new ways of thinking about time, causality, and observation, and why black holes continue to challenge not just equations, but the very idea of what it means to understand the universe. Once space-time was no longer assumed to be fundamental, the information paradox began to reshape concepts that had once seemed untouchable, especially time, causality, and the role of the observer. The conflict between Einstein and quantum mechanics was no longer framed as a battle between equations, but as a clash between assumptions about what reality is allowed to be. Time was the first casualty. In Einstein's universe, time is woven into space-time itself. It flows differently depending on motion and gravity, but it remains a geometric dimension. Events are ordered, causes precede effects. Even in the presence of black holes, time has a clear mathematical structure. Quantum mechanics treats time very differently. In quantum theory, time is not an operator. It is an external parameter. Systems evolve with respect to time, but time itself is not quantized in the same way as position or momentum. This asymmetry has always been uncomfortable, but it was manageable until black holes entered the picture. Black holes force time to fracture. For a distant observer, time near a black hole slows dramatically. Matter appears to freeze at the event horizon, fading and redshifting endlessly. The black hole evaporates over enormous timescales, releasing radiation so slowly that its evolution feels almost static. For an infalling observer, none of this happens. The horizon is crossed in finite time. Nothing special occurs at the boundary. The laws of physics remain local and smooth. Both descriptions are correct. They cannot be reconciled into a single timeline. This was once dismissed as a coordinate artifact, the quirk of relativity. But the information paradox revealed that something deeper was happening. The two descriptions did not merely differ in appearance, they differed in what they claimed existed. From the outside, information must eventually reappear in Hawking radiation. From the inside, information continues toward the singularity. Both claims cannot be simultaneously true in a single space-time picture. This forced physicists to reconsider what time actually measures. In an information-first framework, time is no longer fundamental. It becomes a way of tracking how information is reorganized. Different observers experience different flows of time because they access different slices of the underlying quantum evolution. Time becomes relational. It does not exist independently of observation and information flow. It emerges where information is processed in an orderly way. Black holes disrupt this order. They scramble information faster than any other known system. They push information into correlations so complex that no local observer can track them. As this scrambling occurs, the notion of a single, shared time breaks down. The arrow of time, the sense that the past is fixed and the future is open, also becomes suspect. In fundamental equations, there is no preferred direction of time. The arrow emerges from entropy and information loss. Black holes preserve information but maximize inaccessibility. They create a situation where time's arrow exists for observers even though the underlying laws remain reversible. This distinction resolves an old tension. The universe can be reversible in principle and irreversible in practice. Black holes show how. They preserve the past in correlations that no observer can reconstruct. To observers, the past is gone. To the universe, it is still there. This duality is not a contradiction, it is a difference in scale. Causality undergoes a similar transformation. Einstein's relativity enforces causality through light cones. Nothing travels faster than light. Causes precede effects. This structure is deeply geometric. Quantum mechanics complicates this picture with entanglement. Entangled particles share correlations instantly, regardless of distance. These correlations do not transmit information, but they challenge classical intuitions about separation. Black holes operate at the boundary of these ideas. Information that emerges in Hawking radiation is correlated with what fell into the black hole long ago. These correlations span vast stretches of space-time, yet no signal travels faster than light. Causality is preserved, but not in a classical, localized way. This reveals a deeper principle. Causality does not require locality. Effects can be correlated without being causally connected in space-time. The connection exists in the structure of the quantum state, not in the geometry of space. This insight dissolves many apparent contradictions. Information does not escape from inside the black hole in the usual sense. It is not transmitted through space-time. It is reorganized across the quantum state of the universe. From the perspective of space-time, this looks impossible. From the perspective of information, it is natural. Black holes thus force physics to distinguish between space-time causality and informational consistency. The former is emergent. The latter is fundamental. This distinction also reshapes the role of the observer. In classical physics, observers are passive. They measure what exists. Their presence does not alter reality in a fundamental way. Quantum mechanics weakened this separation by showing that measurement affects outcomes. Black holes push it further by showing that access itself defines what can meaningfully be described. An observer outside a black hole and an observer falling in do not merely see different things. They inhabit different effective realities. The laws they observe are consistent, but the global picture they infer is incompatible. This does not mean reality is subjective. It means reality is layered. Each observer has access to a layer of description that is internally consistent and experimentally valid. No observer has access to all layers at once. The information paradox arises when physics demands a single description that applies to all observers simultaneously. Black holes demonstrate that such a demand is not physically justified. This layered view also clarifies why black holes do not violate the equivalence principle locally. An infalling observer experiences smooth spacetime because at that layer, spacetime is the correct description. The breakdown occurs only when trying to combine layers into a global picture. The paradox is not that physics fails, it is that physics refuses to be compressed into a single story. This realization changes the goal of unification. Instead of seeking one ultimate picture, physics seeks a framework that explains why different pictures coexist without contradiction. Consistency replaces completeness as the standard. This is a subtle but profound shift. It acknowledges that nature may not be representable in a single observer-independent image. It may instead require a network of descriptions, each valid within its domain, connected by precise translation rules. Black holes are where this network is most strained, and therefore most revealing. They show that time, causality, and observation are not absolute. They emerge from how information is structured and accessed. This insight also reframes the meaning of the event horizon. The horizon is not just a boundary in space, it is a boundary in description. It marks where one effective theory gives way to another. Beyond it, space-time language ceases to apply in the same way. This does not make horizons unreal, it makes them contextual. The horizon is real for certain observers and irrelevant for others. Both statements can be true because reality admits multiple layers. Einstein's equations remain correct within their domain. Quantum mechanics remains correct within its own. Black holes reveal where their domains intersect, and where neither alone is sufficient. The information paradox thus becomes a guide to the architecture of physical law. It shows that laws are not arranged in a flat hierarchy. They are layered, with different principles dominating at different scales. Space-time governs where information is organized. Quantum mechanics governs how information evolves. Neither alone can describe black holes completely. This layered architecture is uncomfortable because it resists simplification, but it is also powerful because it preserves consistency without forcing false unity. As physicists began to accept this picture, the tone of the debate changed. The war between Einstein and quantum mechanics softened into something more nuanced. Einstein was not wrong. Quantum mechanics was not wrong. They were incomplete in isolation. Black holes were not destroying information or space-time. They were revealing the limits of each description. The information paradox did not demand that one theory defeat the other. It demanded that physics accept that reality is structured in layers that cannot always be collapsed into one. This acceptance did not end the struggle, it transformed it. Instead of asking which theory is correct, physicists began asking how theories relate, overlap, and give way to one another. Black holes became the laboratories for this inquiry. They forced physics to confront its deepest assumptions about time, causality, and observation, and to replace them with something more flexible, more abstract, and more faithful to the structure of the universe. In the next stage of this exploration, we will see how this layered understanding led to one of the most surprising developments in modern physics: the realization that black holes behave like quantum computers, processing and scrambling information in ways that reveal entirely new limits on computation, complexity, and knowledge itself. Because once information becomes fundamental, black holes stop being mysterious objects in space. They become machines, and perhaps the most extreme ones nature can build. Once physicists began treating information as fundamental, black holes took on a new and unsettling identity. They were no longer just gravitational objects. They became systems that process information in extreme ways. This shift marked another escalation in the war between Einstein and quantum mechanics, because it introduced a new battlefield: computation itself. In classical physics, computation is external. It is something observers do to describe the universe. In the emerging picture of black holes, computation is intrinsic. The universe computes its own evolution, and black holes represent the most extreme form of this process. This idea emerged gradually from the study of entropy and entanglement. Entropy measures how many microscopic configurations correspond to a macroscopic state. In information theory, entropy measures uncertainty in information content. In black holes, these meanings collapse into one. A black hole has the maximum entropy possible for a given region of space. This is not an accident. It means black holes store the maximum amount of information allowed by the laws of physics. No ordinary object comes close. A star, a planet, even a dense neutron star is information poor compared to a black hole of the same size. From an information perspective, a black hole is a saturated system. This saturation has consequences. In the 2000s, physicists began asking how fast black holes process information. The question was not metaphorical, it was precise. How quickly does information thrown into a black hole become scrambled, mixed so thoroughly that it cannot be distinguished from the rest? The answer was shocking. Black holes are the fastest scramblers in nature. They mix information at the maximum rate allowed by quantum mechanics. No system can do it faster without violating fundamental bounds. This result transformed black holes into something entirely new. They were no longer passive absorbers of matter and light. They were active information processors, pushing quantum systems to their theoretical limits. This realization deepened the information paradox rather than resolving it. If black holes scramble information so efficiently, how could that information ever come back out in Hawking radiation? Wouldn't it be lost in a sea of complexity? The answer revealed another layer of the paradox. Information is not lost when it is scrambled. It is hidden. Black holes take simple, structured information and transform it into correlations spread across vast numbers of degrees of freedom. The information remains present but no longer accessible in any localized or interpretable way. This is where complexity enters the story. Complexity is not the same as entropy. Two systems can have the same entropy but vastly different levels of complexity. Complexity measures how difficult it is to reconstruct a state from a simple description. Black holes maximize complexity as well. As a black hole evolves, its internal quantum state becomes more and more complex. Reconstructing the original information would require operations that grow exponentially with the size of the system. Even if the information is preserved, decoding it becomes physically impossible. This distinction matters. The information paradox was never just about whether information exists. It was about whether information remains meaningful. Black holes preserve information while destroying meaning. This resolves the paradox at the level of laws, while preserving the experience of loss at the level of observers. Einstein's spacetime picture never accounted for complexity. It treated systems geometrically, not computationally. Quantum mechanics, by contrast, is deeply tied to information processing. Black holes force these two views to collide. In spacetime terms, nothing escapes the horizon. In information terms, nothing is ever erased. Complexity bridges the gap. Information does not need to travel out of the black hole in a simple, trackable way. It only needs to remain encoded somewhere in the quantum state of the universe. Hawking radiation provides that encoding, but in a form so scrambled that reconstruction is beyond reach. This reframes Hawking's original result. Hawking radiation looks thermal not because information is destroyed, but because the information is buried under layers of complexity. Each particle carries correlations so subtle that they appear random. From a computational standpoint, the radiation is encrypted with a key longer than the age of the universe. This is not a failure of physics. It is physics operating at its limits. Black holes thus reveal a new principle. Physical law does not guarantee computability. The universe may preserve information while rendering it computationally inaccessible. This is a stronger statement than simple irreversibility. It means that even with perfect knowledge of the laws, prediction and reconstruction can fail in practice. This principle has implications far beyond black holes. It applies to chaotic systems, to quantum many-body physics, and even to the limits of artificial intelligence. There are states that exist but cannot be efficiently understood or reconstructed. Black holes are simply the most extreme manifestation of this principle. This also reframes the role of entropy and the second law of thermodynamics. Traditionally, entropy increase is associated with loss of information. In the black hole context, entropy increase corresponds to growth of complexity and inaccessibility, not destruction. The second law becomes a law about accessibility, not erasure. This subtle shift resolves long-standing tensions between thermodynamics and quantum mechanics. It also explains why black holes feel so final. They do not just hide information behind horizons. They process it into a form that is maximally difficult to reverse. Even if the universe remains reversible in principle, black holes ensure irreversibility in practice. This is why the war between Einstein and quantum mechanics could not be resolved by appealing to hidden variables or small corrections. The resolution required introducing new physical notions: scrambling, complexity, and computational limits. These notions do not appear in Einstein's equations. They arise naturally in quantum mechanics. Black holes forced gravity to acknowledge them. This also changed how physicists think about the interior of black holes. Instead of imagining a simple geometric region ending in a singularity, many physicists now think of the interior as a highly complex quantum state. The geometry experienced by an infalling observer is an emergent description of this state, valid only for a limited time and scale. As complexity grows, the geometric description eventually breaks down. This does not mean the observer encounters a dramatic wall or firewall. It means the space-time picture loses coherence as a description. Once again, the paradox dissolves, not by violence, but by abstraction. Einstein's smooth space-time survives where complexity is low. Quantum mechanics governs where complexity dominates. Black holes mark the transition. The information paradox thus teaches that the universe enforces limits not just on speed and energy, but on understanding itself. There are states that cannot be efficiently decoded. There are processes that cannot be reversed in practice. There are histories that cannot be reconstructed. These limits are not imposed by ignorance or technology. They are imposed by physics. Black holes are the clearest evidence. They are not errors in the universe. They are demonstrations of its full computational power. This realization also alters how physicists think about the future of quantum gravity. A complete theory will not just unify forces or quantize spacetime. It will need to account for complexity and computation as physical quantities. Information is not enough. How information is processed matters. Black holes provide the testing ground for these ideas because they push every quantity, entropy, energy, curvature, complexity, to its extreme. They are the stress tests of physical law. As this picture took hold, the war between Einstein and quantum mechanics entered a new phase. It was no longer about which theory was right. It was about which concepts were fundamental. Geometry, it seemed, was not fundamental. Information was deeper, but even information was not the whole story. The way information is organized, scrambled, and processed turned out to be just as important. Black holes revealed that reality is not built from objects or even from information alone, but from processes. Processes that obey strict laws, preserve information, and yet generate outcomes beyond reconstruction. This is why the information paradox refused simple resolution for so long. Physicists were asking the wrong question. The question was never, is information destroyed? The real question was, what does it mean for information to survive in a universe with extreme complexity? Black holes provide the answer. Information survives without remaining interpretable. Einstein's universe was geometric and continuous. Quantum mechanics' universe was probabilistic and informational. Black holes reveal a universe that is computational, a universe where the laws are simple, but their consequences are not. In the next stage of this story, we will see how this computational view of black holes reshaped ideas about horizons, interiors, and the nature of experience itself, and why the final resolution of the paradox required rethinking not only what the universe is made of, but what it means to observe anything at all. As the computational view of black holes took hold, the information paradox entered its most uncomfortable phase. Physics had preserved information, saved quantum mechanics, and reinterpreted spacetime. Yet something still felt unresolved. The equations were consistent, but the experience of observers remained deeply puzzling. This tension centered on a simple question: what does an observer actually experience at a black hole? Einstein's equivalence principle states that a freely falling observer should experience nothing unusual when crossing the event horizon. Locally, gravity disappears, space-time appears smooth. This principle is one of the cornerstones of general relativity, tested and trusted. Quantum mechanics, however, imposes constraints on information that seem to demand something dramatic at the horizon if information is preserved. This conflict came into sharp focus with the firewall argument. The firewall paradox arose from combining three assumptions that each seemed unavoidable. First, quantum mechanics is unitary and preserves information. Second, the equivalence principle holds so the horizon is smooth. Third, effective field theory works near the horizon. Together, these assumptions produced a contradiction. If information escapes in Hawking radiation, then late-time radiation must be entangled with early radiation to preserve unitarity. But near the horizon, that same radiation must also be entangled with interior modes to maintain a smooth space-time. Quantum mechanics forbids this. A system cannot be maximally entangled with two independent systems at once. Something had to break. The firewall proposal argued that the equivalence principle must fail. Instead of a smooth horizon, there would be a violent wall of high-energy particles. An infalling observer would be destroyed instantly. This was a shocking suggestion. It implied that general relativity breaks down at the horizon, not deep inside the black hole, but at a place where curvature can be arbitrarily small. The most trusted principle of Einstein's theory would fail in a region where it should work best. Many physicists resisted this conclusion. Others argued that the firewall was the price of preserving quantum mechanics. Better to sacrifice smooth spacetime than to abandon unitarity. The war between Einstein and quantum mechanics had reached its most dramatic point, yet the firewall paradox depended on treating entanglement as if it lived within a single global space-time description. This assumption was increasingly suspect. The emerging view suggested that space-time itself is an emergent, observer-dependent construct. If so, then entanglement relationships need not be representable within a single geometric picture. This opened a new possibility. Perhaps the contradiction arose not because nature was inconsistent, but because physicists were demanding too much from a single description. This idea became known as black hole complementarity. Complementarity proposed that no single observer ever sees a violation of physical law. An external observer sees information preserved in radiation. An infalling observer experiences smooth space-time. No observer can compare notes. The paradox exists only in a hypothetical global description that no observer can access. At first glance, this sounded like a retreat from realism, but it was not arbitrary. It mirrored principles already accepted in quantum mechanics, where incompatible measurements cannot be simultaneously performed. Complementarity did not deny reality. It denied the necessity of a single, unified narrative. This idea gained strength as holography matured. In holographic models, the interior of a black hole is not an independent region. It emerges from the same quantum degrees of freedom that describe the exterior. The interior description is encoded non-locally in the exterior theory. From this perspective, the firewall paradox dissolves. The radiation does not need to be entangled with two independent systems. The inside and outside are not independent at the fundamental level. They are different descriptions of the same underlying information. The entanglement monogamy violation disappears because the systems are not distinct. This was a profound shift. It suggested that the horizon is not a place where physics breaks. It is a place where descriptions overlap in subtle ways. The smoothness of space-time and the preservation of information are both emergent features, valid in different contexts. The observer's experience remains intact. An infalling observer crosses the horizon without drama because, for that observer, space-time is the correct effective description. The computational complexity of the underlying state has not yet disrupted that description. The breakdown occurs only when attempting to combine incompatible perspectives into a single picture. This layered understanding of reality resolved the firewall paradox without requiring violence at the horizon. It also reinforced a broader lesson. Observation is physical. An observer is not an abstract viewpoint. It is a physical system with limited access, finite memory, and bounded computational capacity. What an observer can experience depends on what information is accessible in their causal patch. Black holes enforce these limits brutally. No observer can access both the full Hawking radiation and the interior space-time. No observer can verify the global entanglement structure. The paradox arises only when physics imagines an impossible observer with unlimited access. Once this is acknowledged, the contradiction evaporates. This does not mean the problem was trivial. It required abandoning the expectation that reality must be describable in a single, observer-independent way. This expectation was inherited from classical physics, where such descriptions are possible. Black holes mark the boundary where this inheritance fails. The information paradox thus reshapes the concept of objectivity. Objectivity does not mean a single global picture. It means consistency across all physically realizable perspectives. Black holes satisfy this requirement. No observer witnesses a violation of physical law. The contradictions appear only in hypothetical viewpoints that exceed physical limits. This reframing also clarifies the role of experience. Experience is not fundamental, it is an emergent phenomenon arising from organized information. As long as information remains organized enough, space-time appears smooth and classical. When organization collapses, experience loses coherence. Black holes represent the ultimate collapse of organization, but only deep inside, beyond the reach of observers. At the horizon, organization still exists at the scale relevant to experience. This is why infalling observers perceive nothing unusual. The firewall paradox taught physics that experience cannot be used as a guide to fundamental structure. Experience is local. The universe is global. Reconciling the two requires careful attention to limits. This lesson also resolves a long-standing discomfort with black holes. For years, physicists worried that black holes were pathological objects that signaled a breakdown of physical law. The information paradox suggested the opposite. Black holes are not where physics breaks. They are where physics enforces its limits most strictly. They enforce limits on speed, They enforce limits on information density. They enforce limits on computation. They enforce limits on observation. The horizon is not a singularity of violence. It is a boundary of access. Einstein's equivalence principle survives because, locally, space-time remains a valid description. Quantum mechanics survives because, globally, information is preserved. Neither theory needs to be destroyed. What needed to be destroyed was the assumption that one description could do everything. The war between Einstein and quantum mechanics did not end with one victor. It ended with a truce enforced by deeper principles. Space-time is emergent. Information is fundamental. Observation is limited. Black holes sit at the intersection of these truths. They force physics to acknowledge that reality is layered, that no observer sees the full picture, and that demanding such a picture leads to paradox. This resolution is not aesthetically simple, it is not comforting, but it is consistent. The information paradox did not demand that physics abandon its principles. It demanded that physics recognize their domains. Einstein's geometry governs experience, quantum mechanics governs information. Black holes reveal where these domains overlap and where they must be kept apart. In the next stage of this story, we will step back from technical arguments and confront the final implications of this truce. We will ask what it means for disappearance, identity, and the fate of objects in a universe where nothing is destroyed, yet nothing remains intact in any recognizable form. Because once the war between Einstein and quantum mechanics ends, the question that remains is not about equations. It is about what it means to exist in a universe that remembers everything and allows almost nothing to be remembered by us. As the conflict between Einstein's geometry and quantum information reaches its final resolution, the information paradox leaves behind a question that is no longer technical but existential. What does it mean for something to persist in a universe that preserves information but destroys form? Black holes force physics to confront the difference between survival and continuity. In everyday experience, persistence means remaining recognizable. A thing survives if it maintains identity through time. When identity is lost, we say the thing is gone. Physics, however, draws a sharper distinction. Something survives if the information that defines it is preserved, regardless of whether that information remains organized in any familiar way. Black holes drive a wedge between these two meanings. When an object falls toward a black hole, it initially behaves like any other physical system. Its atoms interact, its internal processes continue. From its own frame of reference, nothing extraordinary occurs at the horizon, but from the outside, its identity begins to dissolve almost immediately. Its features are smeared, redshifted, and absorbed into the black hole's macroscopic parameters. What remains is not an object, but a contribution. The object's mass, charge, and angular momentum become indistinguishable from everything else that has ever fallen in. The rest of its defining structure disappears from all accessible descriptions. Yet quantum mechanics insists that nothing fundamental has been erased. This forces a redefinition of persistence. Persistence is no longer about identity, it is about encoding. The object persists not as a thing, but as a pattern distributed across degrees of freedom that no longer resemble the original structure. Its information survives without its form. This is deeply counterintuitive because human understanding depends on form. We recognize things by their stable configurations. When configurations dissolve, recognition ends. Black holes expose the contingency of this intuition. They show that identity is not a fundamental feature of the universe. It is an emergent property of low entropy, low complexity states. When complexity grows beyond a threshold, identity ceases to be meaningful, even though information remains. This distinction resolves a long-standing discomfort in the information paradox. Physicists struggled with the idea that black holes could preserve information while appearing to destroy everything that fell in. The resolution is that preservation does not imply preservation of identity. Information survives, objects do not. This reframes the notion of disappearance. Disappearance is not annihilation. It is the loss of recoverable structure. Black holes are not special because they destroy things. They are special because they erase structure more efficiently than any other process. They convert ordered information into maximally scrambled correlations. This scrambling is lawful, unitary, and irreversible in practice. This insight aligns black hole physics with a broader pattern in nature. A burning book does not destroy information at the level of fundamental laws. The information is encoded in heat, radiation, and molecular motion, but the book as a book is gone forever. Black holes perform the same transformation, but perfectly. They take not just macroscopic structure, but microscopic correlations, and scramble them to the maximum degree allowed by physics. This is why black holes feel absolute. They do not violate the laws of physics. They exhaust them. This exhaustion has consequences for how we think about endings. The universe does not end things cleanly. It does not erase histories. It disperses them. Over time, all structure dissolves into correlations that cannot be reassembled. Black holes accelerate this cosmic trend. They are not anomalies. They are previews. In the far future of the universe, even without black holes, complexity grows. Stars burn out. Galaxies drift apart, information spreads, structure fades. Black holes simply bring this future forward. This perspective dissolves the emotional charge often attached to black holes as cosmic destroyers. They are not villains. They are mirrors showing what the universe does naturally when left to its own devices. The information paradox thus becomes a lesson about the limits of permanence. Nothing in the universe is guaranteed to remain recognizable. Only information is guaranteed to persist. This is a subtle but profound shift. It means the universe values consistency over continuity. It preserves the integrity of its laws, not the integrity of its forms. Einstein's spacetime described how forms move and interact. Quantum mechanics describes how information evolves. Black holes force the transition from one language to the other. At low complexity, space-time language dominates. Objects exist. Identities persist. Causality is clear. At extreme complexity, information language takes over. Objects dissolve. Identity becomes meaningless. Causality remains, but only as correlation. Black holes mark this boundary. This boundary also reshapes the meaning of death and destruction in physics. From a fundamental standpoint, nothing ever truly dies. From a structural standpoint, almost everything does. This duality is not a contradiction. It is a reflection of scale. Human intuition evolved in a world where structure persists long enough to matter. Physics operates in a universe where structure is temporary. Black holes force us to confront this without comfort. They show that permanence is an illusion born of limited access and slow change. The information paradox also clarifies why attempts to recover information from black holes are futile. Even if information is preserved, recovery requires reassembling structure from maximal complexity. This is not merely technologically difficult, it is physically prohibited by computational limits. The universe preserves information, but it does not preserve the path back. Once complexity passes a certain threshold, reversal becomes impossible in practice. This threshold defines the boundary between physics as law and physics as experience. Black holes push systems past that boundary instantly. This is why the paradox took so long to resolve. Physicists were trying to preserve not just information, but meaning. They wanted black holes to behave in a way that preserved narrative continuity. The universe does not make that promise, it preserves laws. It does not preserve stories. The war between Einstein and quantum mechanics ended not with one theory defeating the other, but with the recognition that each speaks a different language about different layers of reality. Einstein's language describes organized structure. Quantum mechanics describes information beneath structure. Black holes are where structure collapses into information. This collapse is not violent at the horizon. It is gradual, inexorable, and complete. An infalling observer experiences smooth spacetime because locally structure still exists. The breakdown occurs beyond the scale of experience where complexity overwhelms geometric description. This is why the equivalence principle survives and information is preserved. The cost is the loss of global narrative. This cost is not optional. It is enforced by the laws themselves. The information paradox ultimately teaches that the universe does not guarantee coherence at all levels simultaneously. It guarantees coherence of laws. It does not guarantee coherence of forms. This is the final lesson of the war between Einstein and quantum mechanics. They were not fighting over which laws are correct. They were revealing that laws and forms belong to different layers of description. Black holes tear those layers apart and expose the boundary. Once exposed, the paradox dissolves, not because the universe becomes simple, but because physics stops demanding simplicity. The universe remembers everything, but it remembers in a language that no longer resembles the things we care about. And that is not a flaw in reality. It is the price of consistency in a universe governed by both gravity and quantum law. As the story of the information paradox reaches its final depth, it becomes clear that the conflict between Einstein and quantum mechanics was never truly about black holes. Black holes were simply the place where the disagreement could no longer be ignored. The real conflict was about whether reality itself must remain intelligible to beings inside it. For centuries, physics operated under an unspoken assumption that the universe, however complex, could in principle be understood as a coherent whole. The information paradox quietly dismantles this assumption. It shows that the universe can be fully lawful while remaining permanently opaque in crucial ways. This is not because the laws are incomplete. It is because the consequences of those laws exceed what can be reconstructed by any observer. Black holes demonstrate this more clearly than any other phenomenon. They obey quantum mechanics perfectly. They obey gravity perfectly. And yet they generate situations where information is preserved without being accessible, where history exists without being recoverable, and where reality cannot be narrated from beginning to end. This forces a re-evaluation of what it means for physics to explain something. Explanation no longer means turning reality into a story that can be followed step by step. It means identifying which structures are preserved, which are lost, and why those losses are unavoidable even when nothing fundamental is destroyed. The information paradox thus reframes disappearance as a physical process, not a metaphysical one. Nothing vanishes from the universe, but almost everything vanishes from experience. This distinction is uncomfortable because human meaning depends on experience. We care about what can be remembered, reconstructed, and recognized. The universe does not share these priorities. Black holes make this indifference explicit. They preserve information with absolute fidelity while erasing every structure that would allow that information to matter to an observer. This reveals a quiet truth. Meaning is not fundamental. Meaning emerges only when information remains organized in accessible ways. When organization collapses, meaning collapses with it, even though the underlying information remains intact. This is the deepest resolution of the information paradox. The universe does not forget, but it does not care whether anything remains understandable. Einstein's spacetime provided a framework in which meaning was possible. Objects existed. Events followed one another. Histories could be told. Quantum mechanics preserved information beneath this structure. Black holes expose the limit of this arrangement. They are regions where space-time organization collapses faster than information can remain interpretable. Geometry dissolves into correlations. Objects dissolve into patterns. Narratives dissolve into entropy. This does not signal the failure of physics. It signals the boundary of intelligibility. The war between Einstein and quantum mechanics ended not with victory, but with a concession. That reality is under no obligation to remain comprehensible at all scales. This concession reshapes the ambition of physics. Physics no longer seeks to describe everything in terms of objects moving through space and time. It seeks to describe how descriptions themselves arise and fail. Black holes are the clearest example of description failure that does not imply law failure. They show that space-time is a useful fiction, powerful, predictive, and locally accurate, but not fundamental. They show that information is fundamental, but not necessarily meaningful. They show that observation is constrained, not by ignorance, but by physical law. These lessons extend far beyond black holes. They apply to the early universe, where initial conditions may never be reconstructed. They apply to quantum measurement, where outcomes emerge without preserving full information. They apply to complexity, where simple laws generate behavior that cannot be compressed. Black holes simply compress all of these lessons into one object. This is why the information paradox mattered so much. It was not a technical nuisance. It was a stress test of the assumptions that physics inherited from classical intuition. Those assumptions did not survive. The paradox forced physics to accept that reality can be consistent without being narratable, lawful without being transparent, and complete without being fully knowable. This acceptance does not weaken science, it strengthens it. It prevents physics from making promises it cannot keep. It replaces false completeness with honest limits. The universe does not hide information maliciously, it hides it naturally as a consequence of how information spreads under gravity and quantum mechanics. Black holes are not prisons of information, they are furnaces of complexity. They do not erase, they overwhelm. This perspective also dissolves the emotional discomfort surrounding black holes as ultimate destroyers. They are not places where reality ends. They are places where our ability to track reality ends. Reality itself continues uninterrupted. This distinction matters because it shifts the focus from fear to understanding. The universe is not hostile, it is indifferent. It preserves its laws without regard for whether those laws remain friendly to intuition. The information paradox reveals this indifference in its purest form. It shows that the deepest conflicts in physics arise not because nature is broken, but because our expectations are. Einstein expected spacetime to be fundamental. Quantum mechanics expected information to be sacred. Black holes revealed that both expectations were partially right and partially misplaced. Spacetime is real, but emergent. Information is preserved, but not accessible. Once this is accepted, the paradox dissolves completely. Nothing truly disappears in black holes. Nothing truly remains as itself either. The universe preserves everything it needs to preserve, and discards everything it does not. What it discards is not matter or information, but structure. And structure is where meaning lives. This is the final lesson of the information paradox. The war between Einstein and quantum mechanics was never about which theory would survive. Both survive. What did not survive was the assumption that reality must remain structured in ways that matter to us. Black holes force physics to recognize that structure is temporary, local, and fragile. Even in a universe governed by perfect laws, they show that coherence exists only where information remains organized. Beyond that boundary, reality does not disappear. It simply becomes something we can no longer turn into a story. And physics, at its most honest, accepts that this is not a failure. It is the shape of the universe itself. At the very end of the information paradox, the conflict between Einstein and quantum mechanics resolves into something quieter, but far more profound. What remains is not a contradiction to be fixed, but a boundary to be understood. The paradox taught physics that the universe is not obligated to preserve the kinds of continuity that human understanding depends on. It preserves laws, it preserves information, it does not preserve form, identity, or narrative. Black holes are the clearest demonstration of this principle. They do not erase the past. They dissolve it into correlations so complex that the past can no longer be reconstructed by any observer. History still exists in a formal sense, encoded in the quantum state of the universe, but it no longer exists as a story that can be followed. This is the deepest outcome of the war between Einstein and quantum mechanics. Einstein's theory gave the universe a stage, space-time, where events could be ordered and understood geometrically. Quantum mechanics insisted that information could never be destroyed. Black holes revealed that these two principles can coexist only if the universe allows structure to collapse while preserving information beneath it. Once this is accepted, the paradox no longer threatens physics. It threatens intuition. The universe turns out to be lawful without being legible, consistent without being narratable, and complete without being fully knowable. This realization forces a final redefinition of disappearance. Disappearance is not the destruction of information, it is the loss of recoverable structure. When structure collapses beyond a certain threshold, information becomes permanently inaccessible in practice. No observer can reverse the process. No computation can decode it. No narrative can recover it. Black holes push systems past this threshold faster than any other known process. They are not places where physics breaks. They are places where the limits of understanding become absolute. This is why the information paradox mattered so deeply. It exposed a hidden assumption in science, that preservation implies accessibility, and that explanation implies reconstruction. Black holes refute both assumptions. They show that the universe can preserve everything it needs to preserve, while rendering almost everything meaningless to observers. This does not weaken the concept of reality, it strengthens it by stripping away anthropocentric expectations. Reality does not exist to be understood. Understanding is something that emerges locally, where information remains organized enough to support it. Black holes destroy organization without destroying information. This distinction reconciles all sides of the paradox. Quantum mechanics remains intact because unitarity is preserved. General relativity remains intact because space-time remains smooth where experience occurs. Thermodynamics remains intact because entropy increases through inaccessibility, not erasure. Nothing fundamental is sacrificed. What is sacrificed is the demand for a single global picture. Physics learns to live without it. The war between Einstein and quantum mechanics ends not with a victor, but with a recognition that both theories describe different layers of the same underlying reality. Einstein described how structure behaves when information is organized. Quantum mechanics describes how information behaves when structure collapses. Black holes are the boundary between those layers. They reveal that structure is contingent, temporary, and fragile, even in a universe governed by exact laws. This is not a pessimistic conclusion. It is an honest one. It tells us that meaning, identity, and memory are not guaranteed by physics. They are emergent features that arise only under favorable conditions. When those conditions fail, physics continues without them. The universe does not stop functioning when meaning dissolves. It simply stops being interpretable. This is the final lesson of the information paradox. Nothing truly disappears in a black hole. Nothing truly remains as itself either. Information survives, structure does not, and that difference is everything. Black holes are not cosmic annihilators. They are cosmic translators, converting order into complexity, form into correlation, narrative into entropy. They show that the deepest conflict in physics was never between equations, it was between expectations and reality. Once that conflict is resolved, the paradox dissolves completely. What remains is a universe that remembers everything, forgets nothing, and yet allows almost nothing to be remembered by those who exist within it. And that is not a failure of physics. It is the shape of reality when gravity and quantum mechanics are both taken seriously. At the true end of the information paradox, the final question is no longer about black holes, or even about what kind of universe we inhabit. When preservation and comprehension are no longer the same thing, the war between Einstein and quantum mechanics forced physics to confront an uncomfortable truth. Reality does not organize itself around observers. For centuries, scientific progress reinforced the belief that with enough knowledge, nature would eventually become transparent. Each revolution, Newton, Maxwell, Einstein, quantum mechanics, expanded what could be predicted, visualized, and controlled. Even when theories were counterintuitive, they still offered coherent pictures of what was happening. The information paradox marks the point where that expectation breaks, not because the universe becomes chaotic, not because the laws fail, but because lawfulness does not guarantee legibility. Black holes demonstrate this with ruthless clarity. They obey every known principle of physics. They conserve energy, they conserve information, they evolve unitarily, and yet they generate outcomes that no observer can reconstruct, no matter how advanced or patient. This is not a limitation of intelligence or technology, but it is a limitation imposed by physics itself. The paradox ultimately teaches that there are two kinds of loss in the universe. One kind is forbidden, the destruction of information. The other kind is inevitable, the destruction of structure. Physics forbids the first. Physics enforces the second. Black holes exist precisely where this distinction becomes unavoidable. When structure dissolves into maximal complexity, identity ceases to exist in any meaningful sense. Objects do not persist, histories do not survive, narratives collapse, yet the underlying information remains encoded in correlations so diffuse that recovery becomes impossible. This is not philosophical pessimism, it is a physical statement about complexity. The universe preserves information, but it does not preserve paths back to that information. Once complexity crosses a critical threshold, reversal becomes infeasible even in principle, not because the laws forbid it, but because the resources required exceed what the universe itself can supply. Black holes push systems past this threshold almost instantly. This is why the paradox felt existential. It forced physics to accept that knowing the laws does not imply knowing the outcomes. That determinism does not imply predictability. That preservation does not imply remembrance. These distinctions were always present, but black holes made them impossible to ignore. Einstein's spacetime provided a world where events could be ordered, located, and understood geometrically. Quantum mechanics preserved information beneath that order. Black holes reveal what happens when order collapses while preservation remains. They show that existence does not require recognizability. An object falling into a black hole continues to exist as information, but it no longer exists as an object. Its defining structure is irreversibly dispersed. The universe remembers it without remembering what it was. This is the ultimate resolution of the paradox. Nothing fundamental is destroyed. Everything meaningful is. This distinction reframes how physics understands endings. There is no moment where reality stops. There is no point where laws fail. There is only a gradual erosion of structure until nothing remains that can be tracked, identified, or interpreted. Black holes are not endpoints. They are accelerators of this erosion. This insight also reshapes how we think about the fate of the universe. Even without black holes, the universe trends toward greater entropy and complexity. Stars exhaust their fuel, galaxies disperse, information spreads, structure fades. Black holes simply speed up a process that is already universal. In the far future, the universe may still contain all the information of its past, encoded in radiation and correlations, but it will contain no observers capable of assembling that information into memory or meaning. The universe will remember everything, but there will be no one left to remember. This is not tragic, it is neutral. The universe does not privilege meaning. Meaning is a temporary feature that emerges where information remains organized. Black holes teach physics to separate ontological persistence from epistemic survival. Ontologically, nothing is lost. Epistemically, almost everything is. This separation dissolves the final emotional resistance to the information paradox. The discomfort arose not because physics was inconsistent, but because it violated an unspoken expectation that preservation implies significance. The universe does not make that promise. Einstein's theory never required it. Quantum mechanics never guaranteed it. Only human intuition assumed it. Black holes expose the assumption and discard it. This is why the paradox did not resolve into a simple mechanism or hidden escape route. It resolved into a redefinition of what resolution means. The goal was never to explain how information comes back in a usable form. The goal was to understand why it does not need to. Once this is accepted, the war between Einstein and quantum mechanics ends completely. Einstein was right about space-time where structure exists. Quantum mechanics was right about information at all scales. The conflict arose only when physics tried to apply one language where the other was required. Black holes are the translation boundary. They show that space-time is a temporary convenience, not a permanent foundation. They show that information is permanent but not accessible. They show that observation is local, bounded and fragile. And they show that explanation itself has limits, not limits of intelligence, not limits of mathematics, limits imposed by the structure of reality. This is the final lesson of the information paradox. The universe is not built to be understood in full, it is built to obey its laws. Understanding happens only where structure allows it. Black holes are where structure collapses first. They are not errors, they are revelations. They reveal a universe that is consistent without being comprehensible, lawful without being legible, and complete without being narratable. Once this is understood, the paradox vanishes entirely. Nothing disappears in a black hole, everything disappears as itself. And between those two truths lies the real shape of reality, a universe that remembers everything, forgets nothing, and yet allows almost nothing to be remembered by those who exist within it. That is not a failure of physics. It is the final victory of consistency over intuition, and it is the quiet end of the war between Einstein and quantum mechanics. As the final implications of the information paradox settle, one realization becomes unavoidable. The conflict between Einstein and quantum mechanics was never about which theory is correct, but about what we expect correctness to provide. For most of scientific history, correctness meant predictability, reconstruction, and narrative continuity. A correct theory allowed you to say not only what happens, but how and why it happened, in a way that could be followed step by step. The information paradox quietly dismantles this expectation. Black holes show that a theory can be perfectly correct and still refuse to give you a story. This is the deepest rupture between classical intuition and modern physics. Einstein's general relativity gave us a universe that could be visualized. Even when space-time curved or time slowed, events still lived somewhere. Causes led to effects through geometry. The universe felt graspable. Quantum mechanics replaced certainty with probability, but it preserved something essential: information. Even when outcomes were random, the evolution of the quantum state remained exact and reversible. Black holes force these two achievements into direct conflict and reveal that neither visualization nor reversibility guarantees intelligibility. A black hole is not just a region where gravity is strong. It is a region where description itself fractures. From the outside, a black hole is simple. It is characterized by mass, charge, and spin. Everything else disappears into statistical anonymity. From the inside, space-time continues smoothly, at least for a time. From the fundamental quantum description, neither picture is complete. This fractured description is not a flaw. It is the structure of reality at extreme scales. The information paradox arose because physics insisted on collapsing these perspectives into one unified account. Black holes demonstrate that this insistence is unjustified. Reality does not require a single global narrative. It requires consistency across all physically realizable perspectives. Once this is accepted, the paradox resolves not into a mechanism, but into a principle. Preservation does not imply reconstructability. Existence does not imply identity. Lawfulness does not imply legibility. These principles are not optional add-ons. They are enforced by the same laws that preserve information. Black holes are the clearest environments where these principles dominate. They preserve information perfectly while destroying every structure that would allow that information to be interpreted as a thing, a history, or a cause and effect chain. This reframes what it means to lose something in physics. Loss is not erasure, loss is the collapse of recoverable structure. When structure collapses beyond a critical threshold of complexity, the universe continues to evolve lawfully, but observers lose the ability to track what has happened. Black holes ensure this collapse occurs absolutely. They are not chaotic. They are maximally lawful systems that push lawful evolution to its limits. This is why attempts to save meaning inside black holes always fail. Meaning requires stable structure. Black holes are designed by the laws of physics themselves to eliminate stability. The information paradox teaches that meaning is an emergent luxury, not a fundamental feature of reality. Meaning exists where entropy is low, complexity is manageable, and information remains organized. As these conditions fail, meaning dissolves even though information remains. This is not unique to black holes. It happens slowly everywhere in the universe. Black holes simply do it faster and more completely than anything else. This perspective changes how we think about the role of physics. Physics is not the art of preserving meaning. Physics is the discipline of identifying what must be preserved and what need not be. Black holes tell us that laws preserve consistency, not interpretation. Einstein's equations preserve geometric consistency. Quantum mechanics preserves informational consistency. Neither promises to preserve human categories. The information paradox forced physics to confront this honestly. It also reshaped the concept of completeness. A complete theory does not tell you everything you might want to know. It tells you everything that can be known in principle. Beyond that boundary, silence is not ignorance, it is correctness. Black holes define that boundary. They show that some questions are physically unanswerable, not because the answers do not exist, but because no observer can access the information required to assemble them. This is a profound shift in scientific humility. It acknowledges that explanation has physical limits, not logical limits, not mathematical limits. Physical limits, the universe itself enforces them. The information paradox thus becomes a case study in epistemic boundaries. It demonstrates that knowledge is constrained by space-time, causality, entropy, and complexity. These constraints are as real as energy or mass. Black holes are where all these constraints align. They block causal access. They maximize entropy. They maximize complexity. They enforce observer separation. No single observer can ever assemble a complete description of what happens to an object that falls in. And physics says that this is not a failure. It is expected. This realization resolves the last remaining discomfort with the paradox. Physicists were uneasy not because information might be lost, but because meaning might be. Once it becomes clear that meaning is not a conserved quantity, the discomfort evaporates. Information is conserved. Meaning is not. This distinction explains why Hawking radiation can carry information without carrying identity. Why black holes can remember everything without remembering anything recognizable. The war between Einstein and quantum mechanics ends here. Einstein's space-time governs experience where structure exists. Quantum mechanics governs evolution everywhere. Black holes are the interface where experience fails and evolution continues. This interface is not violent, it is silent. There is no explosion at the horizon, no dramatic annihilation. Just a quiet transition from structure to complexity. This is perhaps the most unsettling aspect of black holes. They do not announce the end of understanding, they simply exceed it. The information paradox teaches physics how to live with that fact. It replaces the demand for global narratives with respect for physical limits. It replaces intuitive completeness with principled restraint. In doing so, it strengthens science, because a science that acknowledges its boundaries is more powerful than one that pretends they do not exist. Black holes mark the outer edge of those boundaries. They are not places where physics stops. They are places where physics becomes honest. At this edge, the universe reveals its final stance in the war between Einstein and quantum mechanics. Both are right. Neither is complete alone. Reality is layered, lawful, and indifferent to whether its structure remains meaningful to those who observe it. Once this is understood, the information paradox ceases to be a problem. It becomes a lesson that the universe is not built to preserve stories. It is built to preserve laws, and those laws, when followed to their limits, lead inevitably to black holes, not as destroyers of reality, but as confirmations of how deeply consistent reality truly is. As the information paradox reaches its final conceptual layer, it reveals something even more fundamental than limits on knowledge or meaning. It reveals that physics itself has a boundary between description and reality, and black holes sit precisely on that boundary. For most of its history, physics assumed that describing reality and understanding reality were effectively the same task. If the equations were correct, then reality could be reconstructed, at least in principle. The information paradox breaks this equivalence permanently. Black holes show that a description can be correct, complete, and internally consistent, and still fail to reconstruct what happened in any usable way. This is not a weakness of theory, it is a property of the universe. The war between Einstein and quantum mechanics forced physics to confront this property honestly. Einstein's general relativity describes space-time as a smooth geometric structure. One of them is the Milky Way. Within that structure, every event has a location, a history, and a causal chain. This makes reconstruction possible. If you know the geometry and the initial conditions, you can trace the past and predict the future. Quantum mechanics replaces certainty with probability, but it preserves something crucial: the exact evolution of the quantum state. In principle, nothing is ever erased. The past is always encoded in the present. Black holes preserve both principles, but only by severing the link between encoding and reconstruction. This severing is the heart of the information paradox. The universe keeps perfect records while destroying every practical method of reading them. This forces physics to accept a distinction it had long resisted. There is a difference between what exists and what can be decoded. Black holes are not special because they hide information. Many systems hide information. Black holes are special because they hide it optimally. They do so by pushing complexity to its maximum. As complexity grows, the resources required to decode information grow faster than any physical system can supply. Eventually, decoding becomes impossible not because of ignorance, but because the universe itself lacks the capacity to reverse the process. This is a physical boundary, not a technological one. Once this boundary is crossed, reconstruction is gone forever. Black holes cross it immediately. This changes the meaning of determinism. The universe may be fully deterministic at the fundamental level. Every state follows precisely from the one before it. But determinism no longer implies predictability or reconstructability. The laws are exact, the outcomes are opaque. This is the final reconciliation between Einstein and quantum mechanics. Einstein gave us a deterministic universe. Quantum mechanics gave us a unitary universe. Black holes show that determinism and unitarity can coexist with permanent opacity. This was never anticipated. It requires abandoning the idea that physical law must remain accessible to reasoning creatures. The universe does not privilege observers. It does not care whether its evolution can be followed. It only cares about consistency. The information paradox forced physics to internalize this indifference. Once internalized, many lingering anxieties dissolve. Black holes no longer threaten quantum mechanics because information is preserved. They no longer threaten relativity because space-time remains smooth where it must. They no longer threaten causality because no observer can exploit correlations to send signals backward in time. What they threaten is the assumption that physics must remain narratable. That assumption dies here. This has consequences for how future theories will be judged. A theory of quantum gravity will not be complete because it produces intuitive pictures. It will be complete because it correctly identifies what can and cannot be described. It will tell us not only how reality behaves, but where explanation must end. Black holes provide the template. They show that the correct response to paradox is not always to fix the universe, but sometimes to fix our expectations of it. The information paradox existed because physicists expected three things to coexist: global space-time description, local experience, and unitary information flow. Black holes demonstrate that you can have any two, but not all three at once in a single picture. The resolution is not to sacrifice one principle, but to abandon the demand for a single picture. Reality is not flat, it is layered. Each layer is internally consistent. No layer tells the whole story. This layered structure is not an aesthetic choice. It is enforced by the laws themselves. Black holes are where the layers separate cleanly enough to be seen. At one layer, space-time exists and experience is smooth. At another layer, information evolves unitarily without reference to geometry. Trying to merge these layers into one narrative creates paradox. Allowing them to coexist dissolves it. This is the ultimate lesson of the war between Einstein and quantum mechanics. They were never incompatible. They were incomplete when forced to speak the same language. Black holes reveal that physics requires multiple languages, each valid within its domain, none sufficient alone. This insight also reshapes how physics understands truth. Truth is no longer a single picture of reality. It is a network of consistent descriptions connected by precise limits. A statement can be true in one description and meaningless in another. This is not contradiction, it is context. Black holes demand this maturity from physics. They punish overreach. They expose unjustified assumptions. They reward restraint. The information paradox thus becomes a guide for how science should proceed at its limits. Do not demand global narratives where none are physically accessible. Do not equate preservation with retrievability. Do not mistake local experience for fundamental structure. These are not philosophical cautions. They are physical requirements. The paradox also teaches that loss is not fundamental, but neither is meaning. Meaning depends on structure. Structure depends on low complexity. Low complexity is temporary. Black holes simply compress this truth into a single phenomenon. They show that the universe preserves what it must preserve, information and law, and discards what it does not need, identity, narrative, coherence. This is not cruelty, it is neutrality. The universe is not hostile to understanding. It is indifferent to it. Understanding happens where conditions allow it. Black holes mark where they do not. This recognition completes the resolution of the information paradox. Nothing disappears in violation of quantum mechanics. Nothing survives in violation of experience. Both are true because they apply to different layers of reality. The war between Einstein and quantum mechanics ends here, not with victory or defeat, but with a boundary. On one side lies space-time, experience, and story. On the other lies information, evolution, and law. Black holes are the seam where the two meet, and where the illusion that they must merge finally collapses. What remains is not mystery, but clarity about limits. And that clarity is not a loss. It is the deepest form of understanding physics can offer. At the very edge of the information paradox, when every technical argument has been exhausted and every mathematical escape route has been explored, physics is left with its most uncomfortable conclusion. The universe is allowed to be exact without being interpretable. This is the final implication of the war between Einstein and quantum mechanics. For generations, physics progressed under a quiet assumption that reality, however complex, ultimately submits to explanation. Even when theories became abstract, they still promised that with enough effort, the universe could be reconstructed, that the past could be traced, the future predicted, and the present fully described. Black holes break that promise, not because they violate laws, but because they obey them too perfectly. The information paradox shows that physical law can be complete while explanation fails. The universe can preserve everything that matters to its equations while abandoning everything that matters to understanding. This forces a radical separation between physical existence and conceptual access. Einstein's spacetime gave existence a shape. Events happened somewhere. Histories could be drawn as lines. Causes flowed through geometry. Quantum mechanics added probability but preserved exact evolution beneath uncertainty. Black holes reveal what happens when existence continues without shape. They are regions where the universe keeps perfect accounts while erasing every feature that would allow those accounts to be read. This erasure is not violent, it is systematic. Information is not destroyed, it is dismantled, broken into correlations so numerous, so deeply entangled that no observer, no matter how powerful, can reverse the process. This dismantling introduces a new kind of finality. Not the finality of annihilation, but the finality of irreversibility without loss. This distinction is the deepest conceptual shift produced by the information paradox. In classical thinking, irreversibility implied loss. If you could not reverse a process, something must have been destroyed. Black holes show that irreversibility can arise purely from complexity, even when evolution remains perfectly reversible at the fundamental level. The universe becomes irreversible to observers without becoming irreversible in law. This duality resolves the paradox completely, but at a cost. The cost is abandoning the belief that the universe owes observers an explanation. Physics no longer promises that every event can be unpacked into a meaningful sequence. It promises only that every event follows from the laws. Black holes are where this promise is tested and upheld. They demonstrate that laws are more fundamental than narratives. Narratives require structure. Structure requires low entropy and manageable complexity. Black holes annihilate structure while respecting law. This is why they appear so hostile to intuition. They are not chaotic, they are too ordered. They push lawful evolution to a regime where interpretation collapses. The information paradox thus becomes a boundary marker for science itself. On one side of the boundary lies classical explanation, objects, trajectories, histories, identities. On the other side lies fundamental evolution, quantum states, correlations, entanglement, unitary flow. Both are real, but they are not simultaneously accessible. Einstein's space-time belongs to the first side. Quantum mechanics governs the second. Black holes force physics to confront the seam between them. This seam is not smooth. It is where explanation fractures. Once this is accepted, the lingering discomfort around black holes disappears. They are no longer mysterious destroyers or paradox generators. They are limit cases, demonstrations of what happens when the universe is taken at its word. They show that physics does not care about recognizability, it cares about consistency. This lesson reshapes the meaning of scientific completeness. A complete theory does not explain everything we can imagine, it explains everything that can be physically accessed. Beyond that, silence is not ignorance, it is accuracy. Black holes define that silence. They tell us where explanation ends, not because we lack insight, but because insight itself becomes physically impossible. This is not a retreat from realism, it is a deeper realism. It recognizes that reality is not constructed to be transparent to the systems within it. Observers are physical systems subject to the same constraints as everything else. They cannot step outside the universe to survey it as a whole. Black holes enforce this humility absolutely. No observer can see both the full Hawking radiation and the interior space-time. No observer can verify the global entanglement structure. No observer can reconstruct the full past of an object that has crossed the horizon. These are not accidents. They are enforced by causality, entropy, and complexity. The information paradox thus teaches that knowledge itself is a physical quantity, limited, localized, and constrained by the same laws that govern matter and energy. This realization dissolves the last trace of the war between Einstein and quantum mechanics. Einstein's theory governs the domain where knowledge can be organized geometrically. Quantum mechanics governs the domain where knowledge dissolves into correlations. Neither theory is wrong, each becomes incomplete when forced beyond its natural domain. Black holes are the clearest demonstration of this division. They show that space-time is not the container of reality but a phase of it. They show that information is not meaning but the substrate beneath it. They show that observation is not fundamental but emergent. Most importantly, they show that the universe can be perfectly lawful without being interpretable. This is the final philosophical shock of the information paradox. It overturns the idea that understanding is the natural endpoint of science. Understanding becomes conditional, possible only where structure survives. The universe does not guarantee that condition everywhere. Black holes are the proof. They preserve information but destroy interpretation. They obey every law but defy every story. They are exact, silent, and complete. In this sense, black holes are not anomalies, they are revelations. They reveal that the deepest layer of reality is not built from objects or events, but from evolution, a continuous unitary transformation of information that does not pause for comprehension. Einstein gave us geometry. Quantum mechanics gave us information. Black holes reveal evolution without interpretation. This is the final resolution of the paradox. Nothing ever truly disappears. Nothing ever truly remains intelligible. Between those truths lies the real universe, consistent, indifferent, and unconcerned with whether its workings can be turned into narratives. The war between Einstein and quantum mechanics ends here, not in reconciliation, but in clarity. Clarity about what physics can promise, clarity about what it cannot, and clarity about the fact that the universe does not fail when explanation ends. It simply continues, exact, silent, and complete. At the final horizon of the information paradox, physics is forced to confront a truth that lies deeper than equations, deeper than theory, and deeper than paradox itself. Reality does not privilege comprehension. This is not a statement of defeat, it is a statement of structure. For centuries, the success of physics created a powerful illusion that the universe is not only lawful but ultimately decodable. That with sufficient intelligence, time, and mathematical precision, every process could be unfolded, every past reconstructed, every future predicted. Black holes are where this illusion finally collapses. They do not collapse it by breaking laws. They collapse it by obeying them too completely. The information paradox reveals that the universe can be exact while remaining permanently opaque, not because something is hidden, but because nothing is simplified. Einstein's universe was built on continuity. Space and time formed a smooth fabric, events had locations, causes had paths. Even the most extreme predictions of general relativity still respected a form of geometric intelligibility. Quantum mechanics shattered classical intuition but preserved a deeper promise, reversibility. Beneath probability, the quantum state evolves precisely. Nothing is erased. In principle, the past is always present. Black holes honour both theories. and yet they expose a boundary neither theory alone could reveal. They show that reversibility does not imply retrievability. Information can be preserved in a way that makes recovery physically impossible, not because the laws forbid it, but because the universe refuses to compress complexity back into structure. This distinction is subtle, and it is the key to everything. The universe preserves information as correlations, but correlations do not automatically form narratives. Narratives require hierarchy, locality, and scale separation. Black holes annihilate all three. They flatten hierarchy, they destroy locality. They eliminate scale separation. What remains is information without scaffolding. This is why the information paradox felt so disturbing. It was never about whether physics was wrong, it was about whether physics still spoke our language. The answer, revealed slowly and painfully, is no. Physics speaks the language of consistency, not comprehension. Black holes are where this becomes undeniable. They take structured information, objects, histories, identities, and dissolve it into a quantum state that remains exact but no longer supports interpretation. The universe remembers everything while refusing to tell the story of what it remembers. This is not an accident, it is a consequence of how information behaves under gravity. Once information density reaches its maximum, the universe cannot preserve structure without violating its own laws. Something must give. And what gives is meaning. Meaning is not conserved. Identity is not conserved. Narrative is not conserved. Only information is. This realization closes the final gap in the paradox. Physicists were not disturbed by the idea that information might be hidden. They were disturbed by the idea that nothing meaningful could ever be recovered. Black holes confirm that this disturbance is justified and unavoidable. The universe does not care whether its records can be read. This shifts the purpose of physics itself. Physics is no longer the pursuit of ultimate explanation in the narrative sense. It is the pursuit of boundary identification, understanding where explanation is possible and where it must end. Black holes are not problems to be solved. They are boundaries to be recognized. They mark the edge where space-time ceases to be a useful description, where identity dissolves, where causality becomes correlation, and where explanation gives way to evolution. This is not a failure of unification, it is the deepest form of unification possible. Einstein and quantum mechanics are unified not by forcing them into one picture, but by recognizing where each picture applies and where it must be abandoned. Einstein governs experience. Quantum mechanics governs evolution. Black holes govern the transition. This transition is silent. There is no explosion at the horizon. No dramatic annihilation, just a steady loss of structure until nothing remains that can be tracked, followed, or understood in human terms. This silence is perhaps the most unsettling aspect of black holes. They do not announce the end of understanding. They simply pass beyond it. The information paradox teaches physics how to accept this without mysticism or despair. It shows that truth does not require accessibility. A statement about the universe can be true even if no observer can ever verify it. This is not an epistemological loophole. It is a physical consequence of causality and complexity. Black holes enforce this consequence absolutely. No observer can access both sides of the horizon. No observer can reconstruct the full quantum state. No observer can compress maximal complexity back into narrative. These are not limitations of knowledge. They are limitations of reality. The final reconciliation between Einstein and quantum mechanics occurs here. Einstein's demand for smooth local physics is respected. Quantum mechanics' demand for information preservation is respected. What is abandoned is the demand that reality remain globally interpretable. Once that demand is released, the paradox dissolves completely. There is no contradiction. There is only a boundary, and that boundary is not arbitrary. It is enforced by the same laws that make the universe stable, consistent, and predictable where prediction is possible. Black holes do not undermine science. They mature it. They force physics to distinguish between what must be preserved and what cannot be demanded. They replace naive completeness with principled limits. They teach that understanding is local. It exists where structure exists. Beyond that, physics continues without it. This is the final philosophical weight of the information paradox. It tells us that the universe does not exist to be understood, and that this does not diminish it. Understanding is a phenomenon that emerges where conditions allow it. Black holes are where those conditions fail most completely. The universe does not collapse there. It continues flawlessly. The war between Einstein and quantum mechanics ends not with synthesis, but with acceptance. Acceptance that laws are deeper than stories. Acceptance that preservation is deeper than meaning. Acceptance that reality is exact even when it is silent. Black holes stand as monuments to this acceptance. They are not mysteries waiting to be solved. They are truths waiting to be recognized. And once recognized, the information paradox is no longer a paradox at all. It is the clearest message physics has ever delivered about the limits of understanding and the integrity of the universe beyond those limits. At the absolute end of the information paradox, nothing dramatic happens. There is no final equation that resolves everything, no sudden revelation that turns confusion into clarity. What happens instead is quieter and far more definitive. Physics learns where it must stop asking certain kinds of questions. This is the true resolution. The paradox dissolves not because we discover how information comes back in a form we can recognize, but because we finally accept that recognition was never guaranteed. For a long time, physicists assumed that if the universe preserved information, then in principle the universe preserved meaning. That assumption was never written into any equation. It was inherited from intuition. Black holes expose it as false. The universe preserves information because quantum mechanics demands it. The universe does not preserve structure because nothing demands that it should. This distinction is the final line drawn by the information paradox. Einstein gave us a universe where structure mattered. Space-time organized events. Objects followed trajectories. Causes led to effects through geometry. Meaning was implicit in the way reality was arranged. Quantum mechanics went deeper. It stripped away certainty but kept something sacred underneath, the exact evolution of the quantum state. The universe at its core remembered everything. Black holes force these two views to coexist without compromise. They preserve information perfectly while destroying every framework that would allow that information to remain intelligible. This is not a contradiction. It is a hierarchy. Information sits deeper than structure. Structure sits deeper than meaning. Black holes erase upward, not downward. Once structure collapses, meaning collapses with it. Information remains, but it no longer refers to anything recognizable. This is why black holes feel final even though nothing fundamental ends. They do not end existence, they end interpretation. This is the subtlety that haunted the information paradox for decades. Physicists were not afraid that information might vanish. They were afraid that everything we care about might, and black holes confirm that this fear is justified, but not because the universe is broken. Because the universe is indifferent. Indifference is not hostility, it is neutrality. The universe does not target meaning, it simply does not preserve it when preservation is no longer compatible with its laws. Black holes are not exceptions to this rule. They are its purest expression. They show that the universe has no obligation to remain legible to the systems within it. This realization forces a final transformation in how physics understands itself. Physics is no longer the search for a complete story of reality. It is the identification of what survives lawful evolution and what does not. What survives? Information, consistency, unitary evolution. What does not survive? Objects, identity, narrative, meaning. Black holes sit exactly at the boundary between these two lists. They preserve everything that physics requires to remain preserved, and destroy everything that physics does not promise to protect. Once this is understood, the war between Einstein and quantum mechanics is truly over. Einstein was right about local experience. Quantum mechanics was right about global evolution. They were never meant to produce a single, universal picture that works everywhere. Black holes reveal where that expectation fails. They show that space-time is a phase, not a foundation. They show that information is fundamental but not interpretable. They show that observation is local, fragile, and temporary, and they show that explanation itself has a horizon. This horizon is not located in space, it is located in complexity. Beyond it, the universe continues exactly as the laws demand, but no observer can follow. This is not a failure of knowledge. It is a physical limit on what knowledge can be. The information paradox does not end with reassurance. It ends with honesty. Honesty that the universe is not built to preserve stories. Honesty that preservation does not imply remembrance. Honesty that laws matter more than meaning. Black holes are the final proof. They are not places where reality ends. They are places where understanding ends while reality continues, and that is the deepest resolution physics can offer. Nothing truly disappears. Nothing truly remains recognizable. Between those truths lies the real universe, exact, lawful, indifferent, and complete. Once this is accepted, the information paradox is no longer a problem. It is a boundary, and boundaries once recognized are not mysteries. They are truths. This is where the war between Einstein and quantum mechanics finally ends. Not with victory, not with defeat, but with clarity about what the universe is willing to give us and what it never promised to give at all.